In this video lecture, we will shortly discuss the hybrid PV multi-junction based on thin film silicon PV and organic PV that has been developed in a collaboration between Delft University of Technology and Eindhoven University of Technology in the Netherlands. I will use this device architecture as an example how to design process of a solar cell device taking place on experimental level. In PV2X, we have discussed the concept of multi-junction solar cells for various PV technologies. In the shown figure, the evolution of the record efficiencies for organic, single, tandem and triple solar cells are plotted up to 2015. In 2015, the record efficiency have gone from 11.3 for a single junction up to 11.8% for a triple junction. And we have discussed the best initial efficiencies for the thin film silicon multi-junction devices. These numbers show that the gain in going to a triple junction for a thin film silicon device is larger, going from 11.9% for a single junction up to 16.3% for a triple junction is an absolute gain of 4.4%. For OPV, on the other hand, up to 2015, the gain was marginal with 0.5% going from 11.3% up to 11.8%. Last week we discussed that the bandgap energy utilization of high bandgap organic materials is relatively poor as demonstrated in this plot. A high bandgap silicon alloy like amorphous silicon has the same shortcoming. These silicon alloys don't have a very high utilization of bandgap energy either. However, we can see in this graph that it's still better than what has been achieved for organic high bandgap materials. Therefore, we have developed the experiment to explore the potential of organic multi-junctions. What efficiencies can be achieved if one would have an organic high bandgap material with higher values for the VOC? This means replacing the high bandgap organic material by an amorphous silicon absorber material. Therefore, a hybrid multi-junction in which we have a top cell and or middle cell based on amorphous silicon and a bottom cell based on organic materials needed to be developed. For these experiments, three different types of amorphous silicon have been chosen. First, a high bandgap amorphous silicon with a bandgap of 1.73 electron volt leading to an open circuit voltage of 0.98 volts in a single junction solar cell. Secondly, an amorphous silicon with a smaller bandgap of 1.68 electron volt and if integrated in a single junction PIN solar cell leading to an open circuit voltage of 0.95 volts. Thirdly, an amorphous silicon material with the lowest bandgap of all three being 1.6 electron volt, which results in an open circuit voltage of only 0.89 volts in a single junction solar cell. For the low bandgap material, PMD-PP3T PC60BM has been chosen. This is a low organic bandgap material of 1.3 electron volt with a relatively high open circuit voltage of 0.61 volt when integrated in an organic solar cell device. So the amorphous silicon has a higher open circuit voltage in reference to typical high bandgap organic materials, and the low bandgap organic material has a higher open circuit voltage in reference to low bandgap silicon alloys like nanocrystalline silicon. Here you can see a scanning electron microscope picture of the cross-section of a hybrid multi-junction tandem solar cell. As a transparent contact layer on top of the glass substrate, ITO has been chosen. It is rather a challenge to integrate these different technologies in one monolithic integrated multi-junction device. As the amorphous silicon PIN junction is processed at higher temperatures than organic materials, the amorphous silicon top cell needs to deposit it first. The electron collecting layer is zinc oxide and the whole collecting layer for the bottom cell is molybdenum oxide. An extremely thin transparent silver layer is integrated between the zinc oxide and the molybdenum oxide. This layer has the functionality of a recombination layer. On top of these intermediate layers, the low bandgap organic material is deposited. Lithium fluoride is the electron collecting electrode just before the metal contact. In making an amorphous silicon OPV hybrid device, not only the band gap tuning and processing aspects need to be considered. In the next video, we will discuss the optical aspects of such a hybrid device.